So let's continue our salt solution pH analysis by doing the following example problem. And here we're asked to calculate the pH of a 0.30 molar NaF solution. So if we have sodium fluoride, which is NaF, it's a salt, so it's going to fully dissociate into Na plus in aqueous solution plus F minus in aqueous solution. Since we have a full dissociation, if we have a 0.30 molar concentration of NaF, we're going to have a 0.30 molar concentration of Na plus and a 0.30 molar concentration of F minus. Here, Na plus is going to be the conjugate acid of a strong base, so therefore this is going to be neutral. F minus is going to be the conjugate base of HF, which is a weak acid, so therefore this is going to be basic. So if we look into what's happening here, we're going to have F minus in aqueous solution plus water. It's going to be in equilibrium with HF in aqueous solution plus OH minus in aqueous solution. We can then set up an ice table, and we know that our initial concentration is 0.30 for the F minus, 0 for the HF, and 0 for the OH minus. The change in concentration is going to be minus X for the F minus, plus X for the HF, and plus X for the OH minus. At equilibrium, we now have 0.30 minus X, X, and X. So if you notice right here, this is going to be a Kb expression. We're given the Ka for HF. So to get the Kb for this, we know that the Ka times the Kb is going to equal Kw. So our Kb is going to equal Kw divided by Ka. So we can use that value to figure out what we now have for our particular Kb expression. So 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4 is going to give us 1.39 times 10 to the minus 11, which is our Kb. So we can now set up our Kb expression, which is equal to the concentration of X times the concentration of X divided by 0.30 minus X, and that's going to equal 1.39 times 10 to the minus 11. This is a very, very small value, which is great because now we can use the approximation, and that's going to give us X squared divided by 0.30 is going to equal 1.39 times 10 to the minus 11. If we solve for X by multiplying by 0.3 and taking the square root, we get 2.0 times 10 to the minus 6, which is going to equal our concentration of OH minus. So if we wanted to calculate what the pH was, we can first calculate the pOH, which is going to be equal to the negative log of 2.0 times 10 to the minus 6, which the pOH is going to equal 5.69. And then to get the pH, we take 14 minus 5.69 and get 8.31, which is going to be slightly on the basic side, which is what we would predict because we have a conjugate base of a weak acid. So let's kind of go over what we did here. We're asked to calculate the pH of a 0.30 molar NaF solution. We look at that particular salt, look at the cation, look at the anion, and figure out if the cation and anion are going to be acidic, basic, or neutral. So we did that in this case. The Na plus will be neutral. The F minus is going to be on the basic side. So we set up an equilibrium with what's happening. We're going to get our OH minus ions in solution. Here we're given the Ka, but really we need a Kb because that's the expression that we're going to set up. We use the relationship that we derived in a previous video to determine what the Kb is. Then we set up our equilibrium expression. You can use the approximation, solve for the concentration of OH minus, take the negative log of that to get the POH, go from the POH to the pH by taking 14 minus the POH, and our pH for this particular problem is 8.31. So you'll have to use this approach when you're asked to figure out pH of salt solutions.